Hi, this is our 15th lecture, Stochastic Gradient Descent. What we're going to talk about is, not surprisingly, stochastic gradient descent. So, um, so far, we have considered various models and we have considered a few ways to estimate them. With the notion of stochasticity, you're already familiar from training the perceptron algorithm where we fed the data samples one by one to the algorithm. Well, there was a batch algorithm, there was a stochastic algorithm. The syllogistic regression was not trained stochastically, although it was an iterative algorithm, but it was looking at the data all at once. Support vector machines similarly to logistic regression. But um, turns out, and we'll talk about later in this lecture, that not using all the data all at once can have its own advantages, and we will see those in this lecture. And also, we'll find out the details about what does it mean to use stochastic gradient descent, a little bit of recent findings, relatively recent findings, maybe the last 5 years, or maybe more. And the importance of stochastic gradient descent for large data computation, as well as approaches that are accelerating stochastic gradient descent and are helping stochastic gradient descent to escape what previously was thought as local minima. So, gradient descent, regular, not stochastic. What is a gradient descent? Is a way to minimize an objective function j of at some point theta. So j of theta is an objective function. Um, oh, okay, that theta point is point in space where our objective function is defined. But theta in the space is a space of parameters of our model. So if our model is perceptron, then j is an objective function, but our parameters are the w, the normal to the vector of the separating hyperplane. If our model is our neural network, then all of the weights of that neural network are our parameters theta. The objective function is the loss that we're minimizing, that single number. But parameters of the model then later will be used where we will find a point in this parameter space where objective function is minimal. And then these parameters at this point that result in the minimum objective functions will be used in our model as the optimal model that we could find. Eta is the learning rate that determines the size of steps we take here. And then our update equation is just, let's, without loss of generality, assume that we're minimizing, and we're minimizing, as they say there, our new value of the parameters is just the old value minus learning rate times the gradient of the objective function. So we want to find a local minima because at local minima, or at local, Actually, we want to find just one. So at a local minimum, the gradient will be 0, and we will not be moving anywhere. That's it, we achieved our goal. Gradient descent. So there are few gradient descent variants, and they differ in what is used as this gradient of the objective function when it is plugged in into the update equation. So one is batch gradient descent. Batch means when all of the data is used to evaluate the gradient and the objective function. So gradient is functional. It takes a function and returns a function. So we have, or yeah, an operator. So we have, when we're saying J, what we are in fact saying is not just a function of the parameters, but it also is a function of our data. And then given the data, given the parameters, we can evaluate the value of our objective. The same about the gradient. It is in fact a function of theta and data. X is the data, theta are the parameters, theta and data. X is a set of all of our samples for I goes to it. The way you organize those samples in X could be a matrix where each column, each row is a sample, could be anything else. For our purposes, a matrix is fine. But what I want to say here is that batch gradient descent takes this complete matrix or this complete set for each evaluation of the gradient at each step. Stochastic gradient descent uses only one sample at a time. Take a sample at some point I, evaluate the gradient, make a step. Mini batch gradient descent evaluate a small sample instead of just x I. It takes x I plus say batch size, a range of samples. The thing is, the difference between the three, besides just looking at this, because they are evaluating the gradient essentially with respect to different data sets each time, the error surface or the manifold on which the action is happening. It's like, imagine a ball sliding along an error surface. For given all of the data, we have an error surface, which is, well, it's, I don't want to say it's true error surface, but that's error surface defined by our data set. When we're taking one element at a time, we're evaluating a totally different function. Instead of evaluating the actual supposedly smooth error manifold, or instead of evaluating the gradient at a point in space, in this theta space, parameter space, of some true error manifold or data defined error manifold or full data defined error manifold rather, we are evaluating gradient with respect to some random or some different error manifold that is defined only for this data point specifically, right? Because if we are if we think about it this way, x sub I, let's fix I to 3. We can, for this particular point, we can fully optimize, take multiple iterations, never change the x, always keep the x, that sample, the same, and find theta that optimizes just for this x, for this one sample. And it will be the optimum, this this theta, this theta that minimizes this function will be different. Let me write in a random place. Will be different from this theta. These two are not the same when you're minimizing with respect to this one sample and the whole data set. We want to find such theta that is in the vicinity of the minimum of this data set or very close to it or is at the same location. Mini batch also gives us yet another estimate if we fix the mini batch, if we fix a sample. For each mini batch, the minimum changes. For each sample, the minimum changes. The key difference is that in the batch gradient descent, when we iterate, we always are taking steps with respect to the same surface. And every step is along the same surface, and we arrive at the minimum. In stochastic gradient descent, each step and a mini batch, each step you end up in a different surface because you're making a step, but then you're taking another step with respect to different surface and yet different surface. And this stochasticity always making a limited decision but making only a step, not fully converging, leads in the end probably to convergence to the same minimum as the batch gradient descent, but only if you're careful. That later. Trade-offs, depending on the amount of data. So the accuracy of the parameter update changes and the time taken to perform an update changes. So batch is accurate, that's as accurate as it can get, but it's slow, it needs a lot of memory, and it can be done online if the data keeps coming in. Um, if we have a lot of data, as happened in 2000s in this century, when we uh, started entering in the era of big data and where we are stuck now for a while. When the data sets are large, terabytes, it's very hard to find RAM where we can put everything. But there is also space complexity that is connected. The larger the data sets are, usually you have to look at each data point at every iteration. So each data set is processed at every iteration. That's a lot. Stochastic, on the other hand, is fast and memory consumption is low and it can be done online. So just take a sample at a time. No need to use any memory. No need to compute for all of the data. Very fast. Mini batch is moderately fast, uses a little more memory. Moderate memory can be done online. Beautiful. Um, Only accuracy may be a problem because if you didn't choose a learning rate good enough or carefully enough, you may never converge and start balancing around the local minimum that in the basin of which you have started. Well, anyways, so batch gradient descent. Let's see how it works. So we want to compute the gradient of j theta with respect to the entire data set. The update equation is the same. The update equation is the same for all of them, but we need to calculate the gradients for the whole data set and perform just one update. For each update, the whole data set, as I said, is involved. For those who understand code better than the words, here's what we have. We just set the number of epochs, and each iteration includes the whole epoch. An epoch is one pass through the whole dataset. Eta is our learning rate. We evaluate the gradient on this whole dataset. Oh, that's an epoch. We made a pass through the whole dataset. And then we update the parameters. And boom, 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 we just make a step that is equals to an epoch, and hopefully we converge given the learning rate and stars are in the right quadrants. So then batch gradient descent has its own advantages. Well, advantages are we're working with the best possible error surface, right? And we guaranteed to converge to a local or global minimum of that surface, global minimum if the function is strictly convex. In all other cases, it's the local minimum, but yeah, even in non-strictly convex functions, but convex functions, we can arrive to sort of global minimum, but distributed global minimum. These advantages can be very, very slow. The more data, the slower it gets. Can be intractable due to memory requirements. When you get the large data, okay, problematic. And no online updates. What about stochastic gradient descent? Great. We need to perform parameter update for each training example x sub I and the corresponding label 1 sub I. Instead of the complete data set, we only use one sample at a time. Update equation is exactly the same, but just now depends only on one sample instead of the whole data set. Okay. For those who understand code better than the words, we still loop through the epochs, however many epochs you want to train for. But the trick is now we just randomly shuffle the data at each epoch. And then because we randomly shuffled, every time we go through an epoch, we always looking at a different sample than we did before. And then for each example in the dataset, we evaluate the gradient just on that example, the tuple of the data and the label, and do an update. Okay, what are the advantages? Usually much faster than batch gradient descent. Can be used to learn online. Disadvantages: performs frequent updates with high variance that cause the objective function to fluctuate heavily. Okay, fluctuations. Look, batch gradient descent would just trace the curvature smoothly. But because our stochastic gradient descent does not actually see that function, it sees a glimpses of it, it bounces around, may end up in the same place, could may end up in a different place. So batch gradient descent converges to the minimum of the basin of the parameters are placed in, and the fluctuation is small. So if you happen to choose a random start for the algorithm near some minimum, or in this kind of attraction basin, if you start here, it'll definitely end up there. That's it. There is no other option. But SGD fluctuations are large, but it may jump over if the fluctuation, one particular fluctuation at one particular step is large, what could happen is, say, if you started here, your batch will definitely end up here. But gradient descent due to stochasticity may end up in a better local minimum. But all of that ultimately complicates convergence to the exact minimum as SGD keeps overshooting. So the stochasticity of SGD is a problem. Learning rate annealing. If we carefully and slowly decrease the learning rate, SGD shows the same convergence behavior as batch gradient descent. So we can make them behave the same, probably. Mini batch gradient descent. Mini batch just says, this fluctuation and uncertainty, stochasticity of stochastic gradient descent is just too much to handle. Why don't we smooth it a little bit by, instead of taking a random step respectfully for each sample, let's just take few samples simultaneously and average their gradients. So instead of one sample pulling north, another pulling south, and another pulling west, we can, like, at this point, each, like, take a few samples and they will be all pulling us in a different direction. But we will sum this gradient up and go in the average direction. So you will take a mini batch of n. For each epoch, we shuffle, and then we iterate through the epoch with the batch size, evaluate the gradient on the batch, and make a step of an update to the parameters, end up in some new, hopefully more interesting place, and continue stepping down towards a local minimum where we will live happily ever after. So mini-batch gradient descent advantages. Mini-batch gradient descent reduces the variance of the parameter updates. As we just saw, the gradient is averaged for all of the samples in the mini-batch, or just added, the averaging part will be handled by the learning rate. Another advantage is we can make use of highly optimized matrix optimizations common to deep learning libraries that make computing the gradient very efficiently. So even if our batch gradient descent is impossible, intractable, because you cannot put the complete terabyte size dataset into GPU memory, but you can still compute everything fast with large enough mini batches so that your GPU queues and pipelines are fully saturated, and everything goes fast, and you go through your epoch very fast because of the fast matrix computation due to the batch sizes. Disadvantages, we have to set the mini batch size. So a little chat on this. Yeah, like sometimes small mini batch size is good. Somewhere there is an optimal mini batch size. But what we're finding, and especially in training models that are very distributed, to play games such as StarCraft, and in um, explorations in studies in the projects like that, we're running multiple models separately in something that is called data parallel mode. Well, in fact, we're running the same model, but every one of the models running on different GPUs or different nodes is only working with their share of data. And there is a notion of something that is called effective batch size. So number of samples each GPU or each network is looking at a time is enough to be to fit in the memory. But after each of those networks, at each GPU in distributed fashion, took the step we average all of the gradients from all of the nodes and only then take the same step everywhere. And this averaging all of the gradients is effectively the same as if we were using a very large batch size that equals to the local batch size times the number of nodes in your distributed network that are doing the training. So challenges. We still don't know how to set the learning rate, right? We need to set the learning rate. It's a hyperparameter. And then remember learning rate annealing. If we anneal, decrease the learning rate carefully enough, we can get to the same point as the batch gradient descent. But how to set this learning rate schedule, unclear. Well, multiple interesting results, and this is more of FYI. Um, one strategy is that you have a learning rate, stepwise learning rate. You keep it at some level for a few epochs, then you drop it, keep it for a few epochs, then you drop it, keep it for a few epochs, and so on. Interestingly, what happens often with the loss, you exhibit this behavior that at the moment when you drop your learning rate, your loss drops dramatically. It is almost as if the model gets in okay, one side note. When I say the model and when we're discussing all of this stochastic gradient descent and gradient descent, it is applicable to any model that we can optimize in a supervised learning fashion and sometimes even unsupervised, but mostly supervised. Uh, Most popular right now are deep learning models, neural networks of various sorts and architectures, but it does not have to be just deep learning. This applies much wider. But the point is, like, if the model arrives, say, imagine our Bayesian or our error surfaces like that. So you had a large step, and the model starts bouncing here. Then you decrease the learning rate, and the model quickly drops and starts bouncing here. And then you decrease the learning rate and the model drops and starts bouncing here, and so on. Just an interesting behavior. Uh, well, recently in the field, we found that instead of that stepwise learning rate, an interesting behavior is to start with a low learning rate and then to increase it uh, slowly to some kind of maximum value before the neural network goes out of control and ends up with numerical overflows and underflows. But then decrease it to zero and then jump up again and decrease it and do in that sinusoidal manner. And interestingly, when you do that, what happens with like it gets stuck and then it goes up and then it gets stuck and then it goes up and then so with this disruptions in your loss, you push your loss up uh, deliberately in that case. The lowest point where the loss gets is lower than where it would have gotten otherwise with a stepwise learning rate and link. Okay, another question is how to change learning rate per parameter. We have so many parameters. Why do we need to assume that they have the same learning rate. Well, and another one is, of course, how to avoid local minima and saddle points. We will learn next about how the field arrived to solutions, some complete, some partial to all of this channel, just even those that are partial still efficient and effective. Okay, there are several algorithms to deal with some problems that stochastic gradient descent introduces and end up with the advantages that it brings. So, SGD problems. If we have a ravine, as you see on the figure, the optimal and fast way to get to the solution would be to continue going down. If you look in this angle, say the ravine goes like that. So despite the optimal way would be to crawl or to just go in large steps along this line. That's I'm kind of trying to give you a perspective. What usually happens if you took a step that is incorrect and just simply doing gradient descent, stochastic gradient descent, you start bouncing around. So let's look at a demo. Hopefully it works for us. Yeah, so you can play with it following the link in my slides that I will provide for you. But let's say we have no momentum here. Momentum parameter is this, and depending on the step size, look what will happen. Um, we will either gonna get stuck here, and the optimum is over there. Let's take larger steps so we can get to the solution. And look what happens. The larger, like if we don't take steps large enough, we keep bouncing around this ravine and then converging to somewhere, but not reaching the optimum. If we take steps that are too large, just nothing interesting happens. We first start bouncing around too much and then just diverge. If the step is too small, don't get far, anywhere far. Well, I guess if we continue it for a while, going with this small step, we will eventually, in a long time, get to the minimum. But let's look at what happens with momentum. How momentum works, I will explain later in this lecture. So let's add some momentum and increase the step size. So we increase the step size, but add momentum. So with some step size, okay, let's increase the step size more, much, enough, more momentum, and we're at the solution practically. So with a momentum term and carefully chosen step size, but large enough, we can arrive at a solution. And that was control. So how does this momentum work? Well, the same idea as in the physical momentum. Uh, Look what will happen to you if you don't fasten your seatbelt. But the same idea is that we want to model our search of the local minimum with rolling a heavy ball along the surface, the error surface. And instead of fluctuating and taking random steps, we want to have some memory or some inertia of where this heavy ball was rolling, even though the roughness of the surface that it's rolling on dictating changes in the direction. If the roughness is small, if fluctuations are small, the heavy ball will just continue rolling and roll over the small changes in the surface, small roughness in the surface. If it is, if the roughness is not roughness, but the actual change, then only then the ball will change the direction. How do we actually emulate it within the frameworks of stochastic gradient descent? And here's how. Instead of doing the update, the regular gradient descent update, or stochastic or not, instead of this, let us accumulate. Instead of making a step, we will keep a variable where we will accumulate with some discounting factor our previous gradient plus the new gradient. So say we're starting, computed the gradient, made this step here. Now our new gradient is this, but our old gradient is telling us to go here, or actually to go here from this point. Well, we will discount this gradient by some factor, and we'll go here instead. So we are changing our direction, but slowly. We're still preserving the tendency of going where we were going before. Let's do this. Let's have E1 equals lambda E0 plus our gradient. Let me just denote this whole thing with nabla. But then V2 is lambda V1. Oh, wait, but this is nothing but lambda V0 plus lambda at gradient 1, gradient 2. But then V3 is nothing but, let's plug in V2. So U 0. So that will be squared 3. Oh no, I think I lost lambda 1 here. Okay, when I plugged it in, I had, okay. That's my mistake. Okay, but and then gradient 3. So you see that we have discounting factors for all of our previous gradients, but we have all of the gradients propagated, and we're kind of making, if we say take lambda 0.9 as here, then this is really small now. This is slightly larger, 0.18, 0.9 gradient, and this is a very small number now. So by doing that, we are actually emulating inertia and emulating a heavy ball rolling downhill and jumping over or avoiding changing the direction too fast. You can play with the demo linked in this on the Distill website, linked in the slides. So momentum is accumulated the farther the ball rolls downhill. The problem with accumulation momentum is that the momentum may accumulate too much of inertia and not stop. We'd like to stop right, like we'd like to go fast. Say we would like to go fast in here, but don't fly over and like end up somewhere there. We still would like to stop at a local minimum. That is favorable. Another interesting approach to this problem of momentum, of how to handle the inertia, how to have advantages of the inertia, but avoid disadvantages, is Nestor of accelerated gradient, or usually called NAG. And so what Nesterov gradient does, you can see it here. Instead, so we are here. Our previous gradient is telling us to go here. Our new gradient at this point. So yeah, this is the point T. We had that other gradient that brought us here. It tells us to go here and continue. But the new gradient is telling us to go here. Before, we would just sum them with some discount factor. What Nestor of accelerated gradient does, as you actually see here, it says, okay, what if we did go just where the inertia tells us to go, the momentum, our our kind of memory of the gradient, and computed the gradient here, where would it point then? And say it points somewhere there. And then we're saying, well, okay, then that's what we computed. We computed the gradient at a point that we would have ended up if we continued our inertia. And we're saying, okay, let's go somewhere in between where that gradient is telling us and where the momentum gradient is telling us to go. So instead of going here, following this gradient, we will end up at this point. So the interesting part about Nestorov's gradient that it probably converges, and it converges in the order of like it converges inversely quadratically, not linearly but sublinearly, right? This is how fast our error decreases with each of our steps. We're making a step according to Nestorov's gradient, and we're getting closer by 1 over step square. Regular gradient is getting closer just by 1 over t. So it's quadratically faster convergence. And very interesting approach, very productive idea. So, but now we want parameter specific learning rate. All of the stuff before that we looked at just set a single number, single learning rate for all parameters, but some parameters change faster, some parameters change smaller, some parameters have a lot of data samples in the data set with those parameters having meaningful values. And if we continue changing everything equivalently, then those parameters that have some value and affect the gradient in the data of the data set, they will affect the gradient the most, while others, rarely observed features, will not affect the gradient at all. So guided by this idea of how do we rebalance this effect of frequency in the data set, was created AdaGrad parameter, AdaGrad approach, adaptive gradient basically. In the adaptive gradient, unlike the momentum, unlike all the previous approaches, what we do, we just keep adding the square of the gradient. So square of the gradient will be just, say if we call this G, then it will be just G transpose G. And we keep accumulating that, and then eta is a single number, and for each parameter, when we when we do that, no, never mind. Yeah, we do not. Yes, so what we actually have is we're squaring the gradient element wise. So okay, we are squaring the gradient element wise. It's still G, but it's every GI squared, and then we're accumulating, just adding and adding all of the previous one. So it's like additive gradient, square of the gradient, and then divided by the dividing by the square root of the diagonals. So we are normalizing our new gradient at the new point by the summation of all of the previous gradient. So it's root mean squared, basically RMS gradient, RMS G, right? Epsilon is just for stability, so we don't divide by 0 if something bad happens, if those gradients go to 0. But what in fact happens is the square root of this this number grows too large, because we're only summing and summing and summing positive numbers, and we don't converge too quick or quick enough. This number grows too large, and we just go to 0, and everything stalls. Nothing changes anymore. No, this gradient, even if it's there, doesn't get to our parameters, and no changes happen. So to address that, to stop this diminishing learning rate in undergrad, Jeff Hinton, is one of his lectures, suggested cure, a suggestion in one of his lectures on Coursera, I believe. But also in parallel, people developing other delta, which we'll see on the next slide, also arrived with the same conclusion. So instead of, if we denote this gradient, the gradient by GT, instead of simply accumulating all of the squares of the gradient as we did in undergrad, what we do a running window average. So now, by adding a discounting factor, we are, as we've seen in the momentum slide, we are discounting our past, and thus, if this is our future in time, and we're doing the averaging, so we're always kind of averaging before in undergrad, everything was averaged with the same coefficient 1. But now there is a fall off. Well, it's actually much faster exponential that I'm drawing here, but still there is a fall off. And with every step, we preserve only some history in this window running average. And this is a root mean square propagation, RMS prop, or a modified version of undergrad, because again, we modify each eta, modify each element of the gradient by normalizing it by square root of, well, this diag is basically what happens. This eta is the same divided by corresponding element of this vector, which is the sum of g squared ith elements, eta, and 0 here, eta divided by, well, sum squared plus fetch factors, so for numerical issues, for numerical stability. But then when you multiply this by the g vector, essentially you simply normalize each element in the g by the corresponding divided, you multiply by eta and divide by the RMS root mean squared gradient. This idea allows independent renormalization of the learning rate depending on how often a sample, how frequent a sample is in the data set. And it also avoids the problem of undergrad of collapse or kind of diminishing learning rate when the sum grows so large that no changes are happening to theta because the gradient has no effect. So people in Ada Delta paper, the author of the Ada Delta paper, observed that the units don't match. Now, if theta has some units, then the update delta theta has some units as well, but those units are not units of theta, because units of delta theta are units of g, but units of g are nothing but units of the partial of j over of partial with respect to theta, but those are 1 over units of theta. But if we look at the proper second order methods with Hessian, the inverse of the Hessian, we see that the units of delta theta, just look at this, the units of delta theta are exactly units of theta, which is nicer. I have to shut down my Siri. Okay, which is nicer. And so they went ahead and introduced another factor, also a moving average. So this is the same as RMS prop. Well, actually, it's a question who was first, because Ada Delta and RMS prop were kind of simultaneously and independently discovered. But Ada Delta added this additional tracking thingy. So we have delta theta, our update, basically the update that includes the gradient, typo, minus 1, t minus 1, the update that includes the gradient, and we're tracking the square of this update, the square average of the square of that update with a moving average, similarly as we did for the gradient. There is a trick that even though for the gradient we can track the instantaneous or the current value, For the update, we cannot, because by this time, this value hasn't been obtained. You have to use, like, you compute the gradient only here. You cannot compute this value yet. But that's technicality. You can do the algebra and arrive at it yourself. So what happens now, we are dividing root mean square of the root mean square of the update and root mean square of the gradient by each other, and multiplying it by the new gradient, the current gradient at t. Learning rate is gone now. It's fully adaptive now, but well, it's a good method, but wasn't fully satisfactory. Uh, I'll show you some results. But the interesting part is the way and the what is tracked. Observing how other grad works, how RMS prop and other delta works, and what is happening with it. Authors of ADAM, adaptive moment method, basically were trying to approximate second order. Well, other delta as well is trying to approximate second order methods, like whereas other grad and RMS prop, they're not trying to approximate the second order methods, the ones that use Hessian or second derivative in addition to the first derivative. But Adam and other delta are explicitly after that. And oh, what Adam is doing, it's tracking a moving average with some decay, with independent decay. It's tracking the gradient, similar to momentum, and it's tracking the square of the gradient. And those two estimates turned out to be biased, so there is this bias correction for those two moving averages that are being tracked, and then the update is similar to RMS update. So Adam turned out to be a very successful algorithm in multiple respects, and actually it works really well with those default parameters. And now by looking at those updates, you can see where the ideas are coming from. And why would we want to model second order methods? So the reasoning is like that. When we study optimization theory, and when optimization theory was developing and is developing, the idea is that it's very easy to get on a local minimum. And so one thing is, okay, if you have a saddle point like that, I'm actually drawing a saddle for you, and you're going by second order, first order method just by gradient descent, you will end up somewhere here, and that's it. Gradient is 0 at this point. But if you had second order information, you would see that in this direction, you could still continue going and you would escape the saddle point. And now imagine that this is just 2 dimensions, but the neural network large model has millions or billions of parameters. That means each parameter is a dimension in the error surface, in the objective space where the objective is defined or loss function is defined. So by chance, to get all of those parameters to have the same, or the surface for all of those parameters to have the same inflection sign, is very difficult. To actually have a local minima, all of them have to curve up. All of the error surfaces of each parameter independently has to curve up, and then you will end up in some kind of a pouch, in some kind of a ball, a little ball, a local minima. But the more of the parameters you have, the more chances that at least one of them will be inflecting into a different uh, direction, and that means you will have more likely than not subtle points rather than local minima. And indeed, we observed when we started putting a lot of effort into training those larger models after Alex Krzyzewski, AlexNet 2012 paper, which attracted a lot of interest to the field. We found out that almost always those models converge to the global optimum, or something like that. All of the optima here are as good as any other. And methods like Adam and Ada Delta and others specifically address this problem of saddle points. By not actually doing second order optimization, we want to um, use any information in the gradients that we can in order to escape the saddle points. So for example, like this division, right, when the gradient converges to zero, this ratio converges to zero as well. But say if you have, yeah, if you will be enforcing the gradient to continue by dividing by normalizing, even if in most of the dimensions of theta the gradient is zero, but in those few that it is not zero, you will keep making uh, keep making progress. Okay, I think that's right. We'll see the examples. So many more methods were developed since then. AdamX, NADAM, AMS Grad, AdamW, QH Adam, Agmo. But if in doubt, just use Adam. It works good enough. You can always, and you have to, if you can't, yeah, if you can't get it to work, you can always go into the literature and read about specifics of each of those other methods if it works for your problem that you're encountering. But frankly, in practice, Adam works quite well. So this is a animation pre-Adam time, and you can see how the Nestor accelerated gradient, Adagrad, Adadelta, and RMS prop compared to the red ball, which is just stochastic gradient descent. Uh, so as you see, RMS prop in this particular example and Adagrad are behaving quite well, and then the magenta color here, Nestor of accelerated gradient catches up. This is a saddle point, by the way, but all of them kind of eventually manage to escape, some faster, some slower, from this saddle point. Well, hmm, interesting. Something went wrong. I can show you the table, but that is okay, not a problem, not a big problem, anyways. Um, the thing is that back in 2007, Leon Boutou and Oliver Bouquet, I think, if I'm pronouncing his last name correctly, published at the Neural Information Processing Systems Conference paper that was stating that now, as we are growing and settling in the region in the uh, uh, times of big data, um, classical batch optimization techniques are infeasible and they require a lot of time and complexity, while stochastic gradient descent has a lot of advantages. And one of the claims was that it not only it is faster to compute, but it actually converges faster, not just because it's taking more steps in the same time, but it actually leads to convergence much faster. And in 2018, in December, when Neural Information Processing Systems is holding their meeting, the now famous conference, the authors were given Test of Time award that 10 years after this paper's predictions actually hold up, and almost everyone in the industry and many people in academia switched to using stochastic gradient descent. That's it for today's lecture.